Okay, so in this video, we're just going to walk through the identical twin scenarios that we looked at previously. So just to set the scene of what we were dealing with here. So we've got a spaceship sets off from Earth for a distant destination. It's traveling in a straight line at a uniform speed at 60% of the speed of light, or 0.6 c. 10 years later, so this is 10 years later as measured on Earth, to be specific, a second ship, captained by the twin of the first captain, sets off in the same direction at 80% of the speed of light. You come across lots of twins when we're doing thought experiments in special relativity because they allow us to compare the ages of things very easily. So the first thing we're going to do is determine when, so at what time, spaceships have traveled equally far or potentially traveled the same distance. So I'm going to use the symbol T to indicate the time since spaceship 1 left. So from Earth's perspective, Captain 1 has traveled a distance of 0.6 t. We're just using speed equals distance over time here. And Captain 2 has traveled a distance of 0.8. So I haven't put the c in here, so this is going to essentially come out and give you light distance of light years or whatever. But anyway, so we've got 0.8, but we're doing t minus 10 because Captain 2 travels for 10 years less than Captain 1 does. So then all we have to do is rearrange our expression and solve for t. So the two ships are going to be at the same location in space 40 years after Captain 1 leaves. So if we illustrate that on a time space diagram like we've got here, we can see Captain 1 was traveling at constant speed all the time. Captain 2 traveled at constant speed, but they started 10 years after. So this is the space-time diagram from Earth's point of view. So we've got this gap of 10 years, and we can see that then spaceship 2 was traveling faster because its line's closer to being horizontal. And then they meet up after 40 years, which would mean we could figure out the distance that they traveled, so 6 times, it was like 24 or whatever. Okay, so that's our kind of diagram to illustrate what's happening. So what we're going to do is determine from Earth's perspective which of the twins is older at that time and by how much. So in order to see how much time has passed for each of Captain 1 and Captain 2's, we're going to need their gamma factors, because that will allow us to relate this 10 years on Earth to the time for Captain 1 and the time for Captain 2. So Captain 1 is at 60% of the speed of light, so we can put 0.6 in here. Captain 2 was going at 0.8 as a fraction of the speed of light. And so we get these two gamma factors here, and I've kept it as an unrounded number. So key thing to remember, a moving clock passes time slower than a stationary clock in the reference frame that we're interested in. So we're in the reference frame on Earth, so the 40 years is like our stationary clock time, if you like. So the Captain 1 and Captain 2 are going to measure less time than this because a moving clock travels slower. So Captain 1 is nice and simple. We just do the 40 divide by the gamma factor because that's what gives us a smaller time. So that's going to be 32 years have passed. Captain 2 is a little bit more fiddly because 10 years pass in Earth's reference frame, so that time isn't affected. The 30 years left, however, would be affected by the gamma factor. So a total time of 28 years passes for Captain 2 as measured by somebody on Earth. So you can see at the other end, we'd expect an observer on Earth to be 40 years older, but Captain 1 is only 32 years older, Captain 2 is only 28 years older, so we've got an age difference of 4 years there. So Captain 2 is 4 years younger, biologically speaking, if you like. Okay, so this has all been done from Earth's point of view. What we're going to do now is switch our point of view and see how that comes out and what that looks like. So we're going to repeat our calculations from the perspective of the first twin. So the first thing I've done is drawn a space-time diagram for what Captain 1 sees. So Captain 1 thinks they're now stationary. So what they think happens is that the Earth and Captain 2 rocket off backwards like this. So they're still going forwards in time, but they think they've shot off backwards, whereas on Earth they think Captain 1 has shot off forward, like. But then Captain 1 will see ship 2 go from being backwards to now being going forwards, because you'll see Captain 2 coming back towards him, and eventually they end up at the same location. Okay. So that's what Captain 1 sees. And to be more specific, Captain 1 would see the Earth and Captain 2 rocket off at 60% of the speed of light, because by symmetry, if Captain 1 is going away at 60% speed of light, the Earth and Captain 2 would be going away at 60% speed of light, so it's actually the same thing. And then they would see Captain 2 come back towards them, but their speed would be not quite what we'd expect, but we'll get to that in a second. Okay, so first of all, how much time passes for Captain 1 before Captain 2 leaves? Now, we know the time measured in the moving, or the moving clock this time, because we know that 10 years is measured on Earth, but Earth is moving in this scenario, so that's our moving clock. So we're going to need to multiply that by the right gamma factor for 60% of the speed of light, and that would give us how long passes on Captain 1's clock, if you like. And you can see in this situation, 12.5 years passes on Captain 1's clock in order for 10 years to pass on the Earth's moving clock. Okay, so then what we need to do is figure out how fast does Captain 2 travel from Captain 1's perspective. Intuitively, you might think that if Captain 1's going at 60% of the speed of light, Captain 2 is going at 80% of the speed of light, then from Captain 1's perspective, Captain 2 would be traveling at 20% of the speed of light. But that's not accurate, because the 60% of the speed of light and the 80% of the speed of light have been measured in different reference frames. So actually, that wouldn't be true, that there's a relative speed of 20%. So we actually have to figure out what the relative speed actually is. So how fast does Captain 2 travel from Captain 1's perspective? And we can do this by figuring out, from Captain 1's perspective, which is what we're looking at, how far does Captain 2 have to travel, and then how long do they have to travel, and we can then figure out the speed. So you can see, from Captain 1's perspective, the distance Captain 2 needs to catch up, or come towards him, is going to be 60% of the speed of light times by 12.5, because that's the time from their perspective. So it's 7.5 light years. So if I miss out the C in here, that makes the distance in light years. So Captain 2 needs to essentially bridge this gap of 7.5 light years. So let's actually mark that on the diagram here. So we know how far they need to travel is 7.5 light years. We also know how long they've got to do it, because we know the whole journey from Captain 1's perspective takes 32 years. I think we know that already, because we calculated that in part 1. We know Captain 2 starts after 12.5 years, so we know the total time that Captain 2 has to travel 7.5. So you can see from Captain 1's perspective, Captain 2 is traveling at just under 40% the speed of light, so nowhere near the 20% we might have intuitively thought. So now we're in a position where we can work out Captain 2's gamma factor from Captain 1's perspective, because we now know the speed, so we can now get the factor which will relate the times. Okay, after that brief interruption. So we can now relate Captain 1's time to Captain 2's time. So let's do that. So remember, from Captain 1's perspective, Captain 2 is the moving clock. Okay, so 19.5 is how long passes for Captain 1. This is just 32 minus 12.5. So if we divide that by the gamma factor, because Captain 2 is a moving clock, we can see that Captain 2's journey time is 18 years from Captain 1's perspective. And its first part of the journey was 10 years, remember, from Captain 1's. This is what Captain 1 thinks Captain 2's time is, giving us a total aging of 28 years, which agrees with our calculation in the first part, which is good, because remember, if we look from different inertial reference frames, we should get the same result. So you can see that Captain 1 agrees that 28 years have passed for Captain 2. An observer on Earth agrees that 28 years passed for Captain 2. So that's good. We've got agreement between the inertial reference frames. So that's a positive thing. Okay, so we're going to look do our final calculations from the perspective of the second twin. And that's going to throw up a problem, and we can discuss why that is. So first of all, a space-time diagram. So what is Captain 2 going to see? Well, Earth is going to be stationary for 10 years, and then Earth's going to rocket backwards. And then it's going to see Captain 1 go away from it, and then it will see Captain 1 come back. And we can see the different times that we have allowed. So we know 10 years is when the Earth changes, and we know the whole journey from Captain 2's perspective is 28 years. Okay, so what we can do is figure out the different stages of the journey. So we can figure out how long passes for Captain 1 during the 10 years. Remember, Captain 1 is the moving clock, so we're going to divide that by 1.25. That gives us 8 years has passed for Captain 1 from Captain 2's perspective. And we can do the second part of the journey as well. So we know that the second part of the journey, once Earth has rocketed off, is 18 years from Captain 2's perspective. So we know that we've moved a distance of 6 light years away. Well, sorry, so Captain 1 has moved a distance of 6 light years away from Captain 2. Why? Because they were traveling at 60% the speed of light for 10 years from Captain 2's perspective. So we can do the 6 light years divided by the time in years gives us a speed 1/3 of the speed of light. We can then calculate the gamma factor for that, which allows us to then work out the time that passes for Captain 1 from Captain 2's perspective. So to get that, I've done the 18 and I've divided it by this gamma factor here, because remember, Captain 1 is a moving clock. And then we get a problem, because we see, hang on, well, if we add 8 to 16.97, we don't get 32. So we've got a reference frame that doesn't agree with the other two, which do agree that 32 is passed. So the question is, why is that? Well, the key is the postulate of special relativity and of general relativity actually is that the laws of physics are the same from any inertial reference frame. And it's the inertial that is key here. So inertial means not accelerating. And you can clearly see that Captain 2's reference frame accelerated, because it was initially, the reference frame was stationary on Earth, so its reference frame matched up with Earth. And then obviously its reference frame changed because, well, from Captain 2's perspective, Earth then went away from it. So we've had an acceleration phase. So therefore, this isn't an inertial reference frame, which is why it doesn't agree with the other two. So when we're doing special relativity, we have to make sure we choose observer reference frames that are inertial. In this case, we didn't, which is why this didn't work and these calculations didn't work out.